mu1 norm of p1 square g is less than or equal to norm of t0 g, and which implies that square of the norm p1 square g is less than or equal to square root of mu1 and square of the norm t0 g. Here we also use the isometry between the g's, and when we define a in this as this term and b as c over the cube of 2 pi k, we can say that square of the norm a1g is less than or equal to a square of the norm t0g plus b square of the norm g. When we take the square root of both sides, we can say that a1g is positive and bounded by this term. But please notice that we just show this inequality is true in the domain of D1, and our aim is to show that this inequality is true for each f in the domain of D01. In the first part of the proof, we found an upper bound on a1g by using our previous knowledge, but in the second part of the proof we need a little bit mathematical background, and I'm not sure that everyone is familiar to convergence, uniformly convergence, and Cauchy sequences. Just I'm trying to explain a little bit. Now, what we know so far, we have the function space D0 and the momentum space D1 is a subspace of D0, and we have a kinetic energy operator T0, and for each f in D0 we can always find a sequence gi such that gi's converges to f and T0 gi's converges to T0f. Now let's see what can we say about the difference between A1GM and A1GM, which corresponds to this line, this blue line. And in the beginning of the slides we say that the absolute value of this term is bounded by A1 Gn minus Gm, and Gn and Gm are in the domain of D1, so we can say that it's bounded by A prime norm of T0 Gn minus norm of it's bounded by A prime norm of T0 Gn minus T0 Gm plus B prime norm of Gn minus Gm. But T0 Gn minus T0 Gm goes to 0, and Gn minus Gm goes to 0. Therefore, this term goes to 0, which means that this blue line goes to 0. As we shown in the beginning, the norm of A1 Gn minus A1 f, which corresponds to blue line, is bounded by the norm of Gn minus f, which corresponds to red line. And this red line goes to 0, which implies that this blue line has to go 0. So, which means that this sequence converges to mean of A1f. So we can say that there's an always subsequence of A1Gn such that this subsequence converges to A1f uniformly. So since Gn's are in the domain of D1, we have this inequality, and the taking the limits gives us this inequality in the domain of D0.